Myself, Koustov Roy, from National Institute of Science Education and Research, Bhubaneswar. So, working under the supervision of Dr. Shubhankar Vedanta. So, the title of my today's talk is Spin Pumping and Inverse Spin Hall Effect in Co3O4. So, the outline of my today's talk will be first, I'll try to give the motivation behind this work, and then I'll try to give some introduction to few fundamentals, and then I'll discuss my results, and then I'll summarize my whole work. So about the motivation of the work, so in case of SOT-based MRAM devices, the two ferromagnetic layers used to be, it has been used, and they are separated by a special layer. When the magnetization direction of the two ferromagnetic layers are in the same direction, that is said to be bit memory 0. And when the magnetization direction of the two ferromagnetic layers are opposite to each other, they are said to be the bit memory 1. Now, in order to access this 0 and 1 state simultaneously in the device case, so what we need to do actually, so on this, below this device, we put a material having a high spin orbit coupling, and we pass a charge current, and due to the spin orbit coupling of this material, a spin current gets generated via the spin Hall effect. And this spin current goes to the free ferromagnetic layer, and the magnetization of this free ferromagnetic layer can be reversed or using this is something called the spin orbit torque. Now, so we can understand the generation of spin current is very much essential in this case. So the spin orbit coupling, when for the material which is high, the conversion rate will also be high. So the standard non-magnet having the high SOC has been used is typically platinum, tantalum, tungsten. Now here we are actually trying to look for the alternative materials which can also have a high spin orbit coupling. So in this work, we are trying to investigate the possibilities of replacing such kind of spin orbit coupling heavy metals with a antiferromagnetic material Co3O4. So as I told that the spin Hall effect is one of the important topic here. So what happens in the case of spin Hall effect when a charge current has been passed through a material having a high spin orbit coupling, the spin dependent scattering happens, and due to the spin dependent scattering, that the one kind of spin goes to the other edges and the other kind of spin goes to the other edges, and in the both edges we could see that the charge neutrality happens. So we could not figure it out how much spin current gets generated here by the electrical method, and the conversion that the spin current density divided by the charge current applied charge current density is known as the spin Hall angle. So if the spin Hall angle is more, the conversion from the charge current to spin current will be more. So the method here which we are using to find out this quantity spin Hall angle is basically the inverse spin Hall effect. So in case of inverse spin Hall effect, we are actually taking a ferromagnetic layer adjacent to this non-magnetic layer, which is having the high spin orbit coupling. Now, in the ferromagnetic resonance condition, a pure spin current basically goes to the non-magnetic layer. And due to the spin orbit coupling of the non-magnetic layer, a charge current gets generated. So it's basically the reverse of the spin Hall effect. So that's why it calls as an inverse spin Hall effect. And also, since we are going to work with the so in case of ferromagnetic resonance condition, the dynamics of the magnetization is governed by this Landau-Lipschitz-Gilbert equation, where the second term is basically the damping-like term. So here there is a constant, something called alpha, which is the Gilbert damping parameter. So when you measure a Gilbert damping parameter for a material, so basically there are a few contributions. So first contribution is the alpha intrinsic. So alpha intrinsic is basically, if we are taking a ferromagnet, non-magnet bilayer system, so alpha intrinsic is the damping part of the ferromagnet itself. And the alpha proximity comes due to the interface of the ferromagnet and non-magnet. And the alpha spin pumping is the vital part of this work, because we are looking for this contribution. So this alpha spin pumping comes due to the spin pumping, and alpha impurity comes due to some physical impurity or the magnetic impurity. Now, if you are talking about a bilayer system, so what we can expect that if my damping of my system is more than a single layer ferromagnet system, so we could say that the spin pumping is present in our case. And the setup which we are using here for the measurement. So this schematic shows, this schematic is basically the standard ferromagnetic resonance measurement setup, where we are using this CPW based method, and where we are while measuring this ferromagnetic resonance spectroscopy, what we are actually doing additional thing, that we are making a contact with our sample here as shown in here, and we are measuring the voltage across this direction using a nanovoltmeter. So basically the simultaneous measurement of the ferromagnetic resonance and this voltage measurement actually happens. So this modified setup is called the inverse spin Hall effect setup. The typical FMR spectra is shown here. This is the FMR absorption spectra. And if you take the FMR derivative, so it basically looks like something like this, where the zero crossing line is something called the resonance field, and the peak to peak position or the line, this is called the line width. So for a certain frequency, for a certain RF frequency, this H resonance and delta H has been evaluated, and it will be used for the evaluation of the damping parameter. Now in this work, the sample structure which we have studied is basically on top of a silicon substrate, we have deposited this Co3O4 of varying thickness, and on top of Co3O4, we have deposited cobalt, and copper we have taken as a capping layer. So here Co3O4 is our material having the high spin orbit coupling, and cobalt is the material which is the ferromagnet here. So, and also the Co3O4 has been deposited via the sputtering method, where we have actually deposited cobalt, and while depositing a cobalt, basically we have put the argon pressure there, and at 150 degrees Celsius, we have deposited this Co3O4. And the nomenclature of the sample is shown here. The first sample, which is the DS1, where cobalt is having the 22 nanometer thickness and copper is my capping layer. And in case of DS2, we have basically introduced now the Co3O4 layer, which is having a thickness 1.25. Now from DS2 to DS6, we are basically varying the thickness of the Co3O4. Our ferromagnetic layer thickness cobalt as well as the capping layer thickness copper is fixed. Now, about the crystallography. So what we have observed in our XRD results for the sample DS6 case, that we could see the Co3O4 peak 220 and Co3O4 peak 400 here, which actually shows that Co3O4 has been grown in a polycrystalline phase. Also, a cobalt peak of 220 is also been observed. And the HRTM image of the same sample also confirms the crystallinity of our samples. And while to evaluate the Gilbert damping parameter, as I told before, that we are basically first we are trying to find out the HR and the delta H resonance field and the line width at different frequencies. Then we have plotted the A versus HR plot here. And that plot has been fitted with the equation 1 shown here, where my gamma is the gyromagnetic ratio, HK is my anisotropic field, and MS is the saturation magnetization. By fitting this F versus H resonance with this equation, we can extract the fitting parameter gamma. And then we have also plotted this delta H versus F for different sample for all the samples, and we can fit with this equation 2, and from this equation 2 we can find out the value of the alpha, which is the Gilbert damping. And the Gilbert damping parameter has been listed in this table as well as we have plotted in this figure. So we could clearly see the x-axis is my the Co3O4 thickness, and the alpha is the Gilbert damping. So we can see that by introducing the Co3O4 layer, the Gilbert damping is basically increasing, which actually kind of predicts that in our sample there are spin pumping is present. And also we have fitted this alpha versus Co3O4 thickness figure with this equation shown here, and where the alpha naught is the damping of the ferromagnetic layer only, and the GR is something called the real part of the spin mixing conductance, and rho NM is called the resistivity of my non-magnetic layer, which is here the Co3O4. By fitting this equation, we could find out something called the spin diffusion length LSD here, which has been found for 2.5 nanometer for Co3O4, and the value is quite higher than the metallic antiferromagnets. In case of metallic antiferromagnets, it has been shown that the spin diffusion length used to be in the range of something near about the 1 nanometer. But in case of Co3O4, where the Co3O4 is something called semiconducting antiferromagnets, so the spin diffusion length is quite large. And also, we also measured the ISHE because, as I suggested that previously, that if the damping value increases, it actually predicts that there can be spin pumping behavior is happening, but we cannot confirm. So in order to confirm the behavior, we measured this inverse spin Hall effect, and we measured this angle dependent inverse spin Hall effect measurement to quantify different contributions, because the measured voltage used to have different contributions. So something, the spin pumping contribution, which is our focus here, and also there can be contribution from the anomalous Hall effect, and there can be contribution from the anisotropic magnetoresistance as well. So for 0 degree case, where my angle is shown as a 0 degree, the angle is shown here, where the V measured is, let's say I'm measuring in the Y direction, and my DC magnetic field in the X direction. So the phi is the angle here. So where phi equals to 0 degree, in that case, the blue circles actually represents the measured voltage here while swiping the magnetic field. So we could see there is a prominent voltage we can see, and while we are rotating the sample by 180 degree, in that case, this measured voltage actually changes the polarity. So it also kind of signifies that there is a presence of spin pumping in our samples. But we want to decouple all the contributions. In order to decouple all the contributions, so this measured voltage has been fitted with this equation shown here, and then we basically extract the symmetric contribution, V symmetric contribution, and the V antisymmetric contribution. So in this way, for each angle, we are basically extracting V symmetric and the V antisymmetric contribution. And also in the below figure, we have seen that there is no kind of voltage for the single layer ferromagnetic layer where there is no Co3O4 layer. Now then, this V symmetric and V antisymmetric has been plotted with the angle phi, and then that plot is fitted with this equation shown here, where VSP is my spin pumping voltage contribution, VAH is the anomalous Hall effect contribution, and this AMR contribution, from it can come symmetric part as well as from the antisymmetric part. By fitting this equation, the fitting parameters are shown here. So we could see that the spin pumping voltage is 3.49 microvolt, and the anomalous Hall effect contribution is minus 1.60 microvolt. So this spin pumping contribution is the dominating contribution in our samples. So for all the samples, we did this angle dependent ISHE measurement, and we extracted all the fitting parameters, which is shown in this table, and also we have plotted these values in this figure as well. So from the figure also, we could clearly see the red spheres, which signifies the spin pumping contribution is the dominating over other rectification components. So the spin pumping is actually dominating in our samples. And then by knowing this spin pumping voltage, we try to figure out the spin Hall angle and the spin mixing conductance of the material. So to find out, we have used the following equation. First, we have tried to calculate the effective spin mixing conductance, which can be calculated with this equation, where delta alpha is the change in damping parameter by introducing the Co3O4. So for individual samples, we calculated the effective spin mixing conductance, and then from there on, we have calculated the real part of spin mixing conductance, and this spin pumping voltage is associated by this equation here, which relates the spin Hall angle. Now we know the VSP for a sample, and we also know the conductivity of the ferromagnetic layer sigma Fm, and we also know the sigma Nm conductivity of the non-magnetic layer as well as the thickness, and Wy is the line width of my coplanar waveguide, and this LSD is the spin diffusion length of Co3O4. So from there on, we can basically calculate the spin Hall angle theta sh, and we could see the spin Hall angle spin Hall angle theta SH is 0.26 for the sample DS2, where the cobalt Co3O4 thickness is 1.25 nanometer. And this 0.26 value is kind of comparable with the other heavy metals like platinum. And at the same time, the spin mixing conductance value is also comes in the order of 10 to the power 18, which is also comparable
just letting
to the
you know,
other.
one more minute.
Yes, sir. I'm just concluding in a few minutes. So this spin mixing conductance is also comparable to the other heavy metals. So which shows that this Co3O4 is a promising material, can be used in the charge current to spin current conversion physics. So as a summary, we have systematically studied the spin pumping and ISHE study, and when we have also calculated the spin diffusion length. And so I want to thank my supervisor, Dr. Shubhankar Vedanta, for giving me the opportunity to work in this topic, and also all the co-workers for this work. Thank you.
Thank you for the great talk. We don't have too much time for questions, but we've got one question in the chat from Sekwon Kim, who asks, why does the resonance frequency decrease as the cobalt oxide thickness increases?
Resonance frequency decreases. No, actually this resonance frequency basically depends, as when she see here from this equation 1, it depends on the anisotropic field here HK, as well as the saturation magnetization. So when we are actually introducing the Co3O4 thickness, maybe the Co3O4 thickness changes the anisotropic field due to the proximity effect. So that can lead to the change in the resonance field decrease with the sample thickness.
Thank you. And Sekwon Kim says thanks as well. I think there might be at least one more question, but we have to move on, unfortunately. So feel free to